Okay, since campus is shut down, thought we'd just all relocate to Hawaii. Yeah, time for 61B. I hope you're doing well. My name's Carlo, and I'm going to be going over exam prep discussion 9 today. And it's all about trees, so I'm going to start off with a little bit of mini lecture on trees, binary trees, tree traversals, quad trees. If you're already comfortable with that, feel free to skip ahead to when I actually go over the problems. So let's talk about what trees are. Let's just start off with that. So a tree is made up of a value that has a set of 0 or more children. And we call this value a node. Okay? Let me define some more terms. The root of a tree is a node that has no parents. The order or degree of a tree is the number of children a node, the order or degree of a node is the number of children a node has. So, number of children node has. And then a leaf node is a node with no children. Awesome. So since each tree's children are also trees, tree problems have natural subproblems that lend itself to recursion. So you're going to find in the preceding discussion and a lot of problems that we deal with regarding trees, we're going to be solving them using recursion. And just tends to be the most convenient, clean solution. However, for essentially all the problems, you can also do them iteratively. So both approaches are still perfectly valid. Okay, a few more terms. Height. Now the height is the largest distance to leaf. So you can talk about the height of a specific node, and that would be the distance from that node to the furthest leaf. Typically we talk about the height of the tree as a whole though, in which case we're talking about the height of the root node to the furthest leaf. And then if you're talking about the depth of a node, so the depth is the distance to the root. So if you have some tree like this, let me sketch something out real quick. The height of this tree would be 3 because the root here, the largest distance to a leaf is 3 if you take this path right here. Okay? So that is 3. Now the depth of like this node here would just be 1 because it has a distance of 1 to the root, or the depth of either of these two nodes would be 3. Okay, now let's talk about a specific subset of trees that we deal with frequently, and you've already probably seen, we've done the binary search tree lab, and that's binary trees. And binary trees are uniquely defined by the fact that every node has either 0 or 2 children. Let me write that down. So you're either a leaf, in which case you have 0 children, or you have 2 children. Now a complete binary tree is something maybe you haven't heard the term of yet, but you've probably seen. This is a binary tree that is completely full at every level. So it looks something like this that I'm drawing out right here. So you can see this tree has 4 levels, and every level is completely full. So complete binary tree is basically completely full in that way, except potentially at the very last level. So if I had like a 5th level, maybe I don't have enough nodes to completely fill it out, but it'd still be a complete binary tree. So why I mention this is just because if you want to know the height of a complete binary tree, that would be, well, let's say n equals number of nodes. So the height of a complete binary tree, as defined above, is a log of n. And we say it's asymptotically equivalent to log of n, because technically you might need to do log n plus 1. It doesn't matter. Now, to find the number of nodes in a complete binary tree, well, to find the number of nodes in any complete tree, so it could be like, instead of binary, it could be tertiary, which is like 3 nodes, or any k unary tree, which has every node has a specific number of children. to find the height, you do branching factor. To find the number of nodes, branching factor to the power of height. So the branching factor is the maximum number of children every node can have. So for a complete binary tree, that would be 2. And then we know the height is log n in this case. So that's 2 to the power of log n. The 2 cancels out the log base 2, so that's just equal to n. So if you use this formula, you'll see you get back to n is the number of nodes. So it's just a good tidbit to be aware of. Okay, let us move on to talking about traversals. Let me scroll down. I'll go to a new page. Okay, awesome. So traversals. So what are traversals? Well, say you want to visit all the nodes in a tree. How we do this is called traversing a tree. So let me draw a little quick example. The left. Okay, awesome. So there's 3 types of traversals that we focused on in lecture, and those are called pre-order, post-order, and in order. So each one of these types of traversals will visit every single node in the tree. They just differ in the order in which they visit the nodes. So with pre-order, you start at the root, and the process is visit node, and then continue traversing your children. So traverse the node's children. With post-order, first you traverse the children, and then you visit node. So if you think about it, like with pre-order, if you're starting at the root, you're going to be visiting the root first and then your children. With post-order, you're traversing all of your children and then visiting your root last. And then lastly, we have in order, and this is defined for binary trees only, whereas pre-order and post-order are defined for all types of trees. So with in order, we traverse the left child, then we visit node, and then we traverse right child. Okay, so let's go through an example with the tree on the right. So for pre-order, you start at the root, okay, and so you visit that. So I'm gonna write down the list of nodes in order in which we visit them. So first it could be 6, and then we're going to visit our children. So we could visit our children in any order. So we could go left first, or we could go right first. When we're talking about these types of problems where you have to list out the ordering, typically we go left first and then right first just to be consistent, so everyone sort of gets the same answer. So we're going to go left, so we visit 3. And then we continue recursively traversing 3's children, and then we visit 0. Okay, at this point, we're stuck because we have no more children. We're at 0. So we go back up to 3 and traverse the rest of 3's children, which would be 2. And then we go back. Now we have no more children at 3, so we go back up to 6, and we traverse the rest of 6's children. So now that's 5, then 4, etc. Well, that's it. Okay. Post-order, I won't go through every single node perhaps, but you'll get the gist of it. First, you traverse the children. So you start at 6, and you don't visit 6 yet. You first go to 3, and then you continue the process. You traverse 3's children before visiting 3 itself, so then you go to 0. Now, 0 has no children, so you just visit that node right away. Okay, so the first node we're going to visit in post order is going to be 0. Then we go back up to 3, and you still want to traverse the rest of its children before visiting 3, so then it would be 2. And then it would be 3 after you visit all of 3's children, etc., etc. And then for in order, we traverse the left child, visit the node, and then traverse the right child. So starting at 6, we go left to 3, then we go left again to 0, And then if we try to go left, we hit null, so we are back up visiting 0. So we first visit 0, then we go back up to 3, and we've already visited the left child of 3, so now we're going to visit 3 itself. And then you go to the right child, this step, so you go to 2, and it is a leaf, so you just go ahead and visit 2, and then etc. You would visit 6, etc. Okay, so I sort of just went through the process manually based off the definitions here, and that's perfectly valid, but there is a sort of shortcut you can use for figuring out the order of traversals. What you can do, so let me change color, is the trick is drawing an outline around the tree counterclockwise. So actually I'll write it out. Here a trick or shortcut, draw outline around tree counterclockwise, and then you add a pre-order visit when you pass to the left of a node, and then you add a post order when you pass to the right of a node, and you add an in order when you pass the bottom of a node. So it'll become a lot less confusing when I actually go through this example. So I'm going to draw an outline around this counterclockwise, starting from the root. So right away, I pass the left side of a node, there's the root node. So I'm going to add like 6 to my pre-order list. So I'm going to visit 6, which is how we did it here before. And then I continue on my way. Boom, again, I pass the left side of a node. I pass the left side of 3, so I'm going to visit 3 for pre-order. And then here I get to 0. I pass the left side of 0. So I would visit 0 now if I were doing a pre-order traversal. And then I loop around, so I'm drawing an outline like tightly around the entire tree. And I've passed the bottom of 0. So now 0 is going to be visited in order. And if I continue wrapping around, I pass the right of 0. So now 0 is going to be visited in post order, right? I'm just following this rule that I've written out here. Okay, so I continue sneaking around, and now I pass the left side of 2, so I'd visit 2. Then I go down the bottom, and the bottom of 2, so I visit 2 for... Oh, sorry, I skipped passing the bottom of 3. So for in order, I would have visited 3, and now I visit 2. Okay, so now I go around again, the right side of 2, so now I'm visiting 2, post order, like etc, etc. So you can just think drawing this out and drawing these like little notches if you want to give yourself a reminder. And doing that process, you can relatively quickly, with some practice, figure out the order in which you're going to visit things. Pre-order, post-order, in order. Okay, let me get back to black. Nice. Okay, so now I'm going to go through the code for, or like the pseudocode for these traversals. And this is called, let me just write it out. So this is called depth first search. Depth first search is the process in which we use to implement this. So it's a recursive function. It takes in a specific node, and I'm going to call the node a tree because that's how it's written out for this discussion worksheet. And then, yeah, we can say if t equals null, then return we do nothing. Okay. Then we recursively call DFS on t.left, so the left child, and DFS on t.right. So you can see this like simple recursive function just starts at some node and calls itself recursively on your left and right children. So just calling this function is going to somehow trace through all the nodes in the tree, and where you do processing will determine whether you are processing them in pre-order, post-order, or in order. So if you visit the node before any calls to DFS, so here, then this would be a pre-order traversal or a pre-order visit. And that matches up our definition. We visit the node here, so we visit T, and then you would traverse T's children, right? So, for example, if here you wrote system.out.println like t.value, then you would print out the values of the tree in a pre-order fashion. So if you passed in this tree on the right, then you'd literally print out 630254 in this pre-order way. Instead, if you do processing in between the two DFS calls, this would be an in-order visit, because you would traverse the left child, and then you would visit, and then you would traverse the right child. Now the last one is post-order, which is visiting the node after traversing all of your children. So this would here would be a post-order visit. Okay. Now, why is this process called depth first search? Well, let me draw another quick example here. The reason being is because we go as deep as possible in our recursion at all times, essentially. So we start at the root, and then we continuously call DFS on t.left. So we're going to go as deep as possible to the left side until we can't go any further because x is now a leaf. And then we'd backtrack back to b, and then we'd go as deep as possible trying to visit all of b's children. And then we'd backtrack once we've visited all of those children, you go back to a, and you try again to go as deep as possible visiting all the children. Okay? So question, what is the runtime of this function? This isn't super important right now, but it's just something nice to keep in mind. So we're going to consider every single edge in the tree because we visit a node and its children. So by going to your children, you're considering those edges, and you're also visiting every node, right? So the runtime is linear in terms of number edges and the number of nodes. Now to keep in mind though, that the number of edges in a tree, so say we have n nodes, then the number of edges is exactly n minus 1. This is always the case. This is a property of trees. So if it's linear in terms of n minus 1 plus n, we can just say it is linear in terms of the number of nodes. Okay? So it's a linear function, which sounds good. You're just trying to iterate through all of the nodes, so it's nice that it just takes runtime proportional to the number of nodes. Okie dokie. That is our big traversals. Now we still have one more traversal to talk about, and that is called breadth first search. Nice. So as opposed to depth first search, which tried to go as deep as possible first, breadth first search is going to explore all of my children before visiting their children. So it's easiest to just explain visually. So we're going to start at the root, and we're just going to visit the nodes from left to right, top to bottom. So we're going to visit A, then we're going to visit A's children, so B and C, and then you're going to visit their children, X, Y, Q, R. So the traversal would be A, B, C, X, Y, Q, R. So you visit all the nodes like one level away from the root, then all nodes 2 levels away from the root, then all nodes 3 levels away from the root, etc. So it's breadth as opposed to depth. Now you can implement this with a queue. I might do a video about this, but it's also, I believe, in the lecture slides, so I'm not going to go over exactly how to implement this quite yet. And then also with a depth first search, you can implement this recursively in this way that I've talked about, but you can also implement it iteratively using a stack. Breadth first search is one of those tree algorithms that is not recursive in fact. So this is done iteratively, like essentially all the time with a queue. Whereas with depth first search, it's most typically seen recursively, but you could also do it iteratively with a stack. Now, if you think about it, doing it recursively is essentially using a stack behind the scenes because you're using stack frames, and just using a manual stack is essentially just simulating what would be done recursively. Okay, so that's it for traversals. Last, we will talk about quadtrees. Okay, let's draw. Okay, quadtrees. So quadtrees, the purpose of them is it's a way to store 2D data. So for a given point, xy, we define 4 regions: northwest, northeast, southeast, and southwest. So say we want some point A here. A divides the 2D region of space into 4 regions. And all points in those regions can be found in one of the corresponding 4 children of A. Okay, so that's the structure. Let me go over an example. Okay, so say we had the point 0, 1 that we wanted to add to our quadtree. Okay, well, 0, 1, that splits up the space into 4 quadrants. Nice. And then I'll just add 0, 1 as the root to our quadtree. Now, say after this we added the point 9, 4, so that's somewhere up here. So 9, 4 is in the northeast quadrant of 0, 1, and it's going to define its own 4 regions within the northeast quadrant of 0, 1. So let me give these letters so I don't have to keep saying the 2 digits. Okay. So if I add now B to the tree, B would be in the northeast quadrant here, and then all the other nodes are null for now. And then now say I added the point 5, 2, so that's somewhere in here, this point C. So C is in the northeastern quadrant of A and the southwestern quadrant of B. And it too will define 2 quadrants within its region, which is enclosed between the regions of A and B, as you can see with the dotted lines. So then C would be down here in the tree. So this quadtree here has a height of 2, and if searching for a given point xy and it isn't in the root, the point of quadtrees is you can narrow down your search to one of the root's 4 children, based off whether xy is northwest, northeast, southeast, southwest. So if you're searching for, 9, 4, starting at the root, you know right away that 9, 4 is in the northeast quadrant of 0, 1. So you know that to go down this path, and you don't have to explore any of the other branches. Now, one thing that will come up in the discussion, so I'm going to preemptively talk about it here, is the order in which you insert points in a quadtree can influence its height. So say you started off with adding the point C first. So like say we had the points A, B, and C in our 2D space, but you first added C to the empty quadtree. So I can draw out visually how that looks here. We're going to have C, and that's the first point we're considering. Then it's going to split up the entire 2D space into its 4 quadrants. And I can draw C there, nice. Okay, and then let's say, at this point it doesn't really matter, let's say we added B, so then B would be somewhere here. So B is in the northeast quadrant of C, so that would go here. And then A would be in the southwest quadrant, so somewhere here. So A would go here. So these two quadtrees here and here have the same number of elements and are representing the same 2D space, but this only has a height of 1 as opposed to this height of 2. And that's because we added C first, which sort of more cleanly divided the 2D space. So it does happen that the order in which you add things influences the height. Using the setters and getters, value left child, right child, but if in a pinch you want to quickly write a binary tree class, you could also just make these public, and then you wouldn't need any of this, and you could just access stuff directly. So if you have new tree, you could do t.left, equals, or print t.value, etc. So that could be faster. Okay. So let's talk about what the first problem is asking us to do. It says, given a binary tree, check if it is a sum tree or not. In a sum tree, the value at each non-leaf node is equal to the sum of all elements present in its left and right subtree. So it's probably easiest to see with the following example. So given any random node, so let's take this 21, we want to check whether this value 21 is equal to the value of the sum of its 2 children. So in this case, its children is 15 here and 6, and then 15 plus 6 is equal to 21, so this checks out. 30, we can see, okay, 21 and 9, that's equal to 30, that checks out. Basically, if we just visited every node and checked this, we would see that, yes, this tree is a sum tree. Okay, so we need to write a function that determines whether an input tree is a sum tree or not. Okay, so this is going to use some of the skills we developed from how to traverse trees in the mini lecture. Essentially, all we need to do is visit every node in the tree and see whether the sum of the node's children is equal to my own value. And then if you're a leaf, then you are a sum tree by default. Okay, so let me write it out. Actually, I might write it out here so we can still see the example. So, I'm going to erase this. Oh, I can't erase. Okay, just kidding. I'll write it out to the left here. Okay, so we have the function public boolean is sum tree, and it takes in a tree t. So here the tree just refers to a specific node, right? So we can assume that they're going to pass in the root node of whatever tree they care about, but this could work with any node. So we can start with the base case. Let's talk base cases. If the tree is, or the node is null, or it's a leaf node, in which case it has no children, then we're going to just go ahead and say that's a sum tree. Okay? So if t equals null, or it's a leaf, so that would mean t dot left is equal to null, and t dot right is equal to null. Then we're going to go ahead and return true. Okay. Now, if it's not a leaf, we need to actually add up the values of its 2 children. So a slight complication with this is we need to check for the case whether you don't have exactly 2 children. You could have 1 child. As the case here, this 9 over here only has 1 child. So if we just added up t dot left, like dot value, the left child might be null, but the right child could have a value. So in the case where one of the children is null, you want to give that child's value a 0. So to do so, we could just use a simple if case. Like we could just define int left equal to 0 by default, and then if t dot left does not equal null, then we'll redefine left as t dot left dot value. Boom. And I'm just sort of scrunching up my work because running out of space. But now it's a similar idea with right. So my right child is null. It'll have a default value of 0. And if not, I'll redefine it. So if t dot right does not equal null, then I'll redefine right to be equal to t dot right underscore equal to, oh sorry, t dot right dot value. Awesome. So now I have left, I have right, and I just need to check if that is equal to t dot value. So I can go ahead and return that as a Boolean. So I can return if t dot value is equal to left plus right. So just returning this would return if like the initial node they pass in is equal to the sum of its children, but you want to check that for every node in the tree. So you can just use this function recursively. If this function works on like a given node, then just apply that on that node's children as well. So I can return this Boolean and the result of a recursive call to isSumTree on both of my children. So I can do and isSumTree of t dot left and isSumTree t dot right. Awesome. Okay, so hopefully that sort of makes sense. We're essentially just traversing the tree because we call a recursive function, like we visit the node. We visit the node by like processing the node here, and then we recursively call isSumTree on both of that node's children. So based off the traversals we were talking about earlier, this could be like characterized as visiting the nodes in pre-order fashion. But for this problem, it doesn't matter what order you visit the nodes. You just need to find some way to visit all the nodes and then check if that node's value is equal to the sum of its children. Awesome. Okay. And again, I have a code for this posted that will be posted on Piazza. Now you might be asking, can you do this recursively? Iteratively? And the answer is yes, of course. Just find a way to visit all the nodes in an iterative fashion and it'll work out cleanly. Okay, for this problem, I'll go over it iteratively to just give you all a sort of taste of how that might look like, but I probably won't do that for all the problems. But you could feel free to skip this following explanation if you want to continue to the next problems. But if you did want to do it iteratively, my approach would just be to, or basically what you need to do, it's 2 steps for an iterative solution. First, you need to add all nodes to a list, okay? And then go through nodes in list and check. And when I say check, I mean check if that node's value is equal to the sum of its children's values. And you can actually combine these 2 steps into one process so you're not going through the tree 2 times. So what I'm going to do is I'm going to start off by creating an array list. that can take in trees. And right here, iterative solution. Okay, and I'm going to go ahead and add, oh, let me call this L, sorry. I'm going to add T to my list, okay. And what I'm going to do is I'm going to process the elements in the list. And by process, I mean check whether that element satisfies the sum tree property. And then after doing that, I'm going to remove the element from the list because I've already processed it. But then I'm going to add that element's children. So I can then go ahead and process its children. So I want to continue doing that for as long as I have new elements to process. So as long as L is not empty, I'm going to go through this for loop. Okay, so while L is not empty, I go ahead and remove, let me call this tree x is equal to L.remove. And it doesn't matter what order you remove them, I'm just going to always remove the first element. And then now x is the node I'm processing. So I want to check whether x's value is equal to the value of its left and right children. So that code is going to be exactly the same as here. So I literally, all this code should be placed here. And instead of using t, I'd be using x because I'm processing x. So I'm not going to rewrite it out, but it's the same thing. So I now have a left, now I have a right. And then instead of this return statement here, instead I'll do if left plus right does not equal to x dot value, and if x is not a child, so, and, I'm sorry, if x is not a leaf, so if x dot right does not equal null, or x dot left does not equal null. The reason why I'm checking if it's not a leaf, if it is a leaf, then you want to say that x satisfies the sum property. So if it doesn't equal the sum of its children and it's not a leaf, then I'm going to go ahead and return false. So you can just stop right away and return false because one of the nodes doesn't satisfy the property. If not, I'll continue going through the while loop. And then after the while loop, once I've visited all the nodes, if I haven't returned false yet, then every node must satisfy the sum tree property, so then I can go ahead and return true. Okay? So hopefully this gives you an idea how you translate things from recursion to iteration. Typically, when we're dealing with tree problems, if you want to do it iteratively, you have to use a data structure. So in this case, we used an array list to store something, whereas with the recursive approach, we didn't need to have any data structure to store things. Okie dokie. Moving on to B, the problem says, given a binary tree, an input list, and an output list, add all the elements in the input list to the output list that appear in the tree. The elements in the output list should be ordered in the same order that would be returned from an in-order traversal of the tree. For example, for the tree in question 1a, if the input list is 15, 9, 8, 36, then after the operation, the output list should be 9, 30, 15, 8, 6. Okay, so with this example, or basically what the problem is asking us to do is go through the tree using an in-order traversal. And as you're traversing the tree, if any of the nodes appear in the input list, then add that node's value to the output list. So for this example, 15, 9, 8, 30, and 6, all of those values in fact appear in the tree. So we just need to add those values. That was 15, 9, 8, 36. So these are the values we're told we care about. We want to traverse the tree in an in-order fashion and then add these values to an output list based off the in-order traversal. So I'm not going to go over in-order traversal again because that was in the mini lecture, But what we do is we first visit our left subtree, then you visit the node, then you visit the right subtree. So in order traversal for this would give us first 9, then we would go to 30, then we would go to 15, then 8, and then 6. So that should be the output. Let me make sure that matches 9, 30, 15, 8, 6. Nice. Okay. So for this problem, we basically just do the code for an in-order traversal, and when we're visiting the node, we're just going to be adding that node to the output list. So a base case, we want to make sure t is not null. So if t is not equal to null, then we're going to go ahead and do our work. So we're going to recursively call sort relative on our left child. So that would be t.left. And then just pass in the same input list and output list. So I'm gonna in this step, I'm recursively traversing the left child, and then I'm gonna recursively traverse the right child. T.right, input list, output list. And then in between those two traversals, I'm going to do my processing. That's what makes it in order. So here that would be if the input list actually contains the value. So if input list dot contains t dot value, then I'm going to go ahead and add it to the output list. Awesome. And that's all there is to it. And the reason, it might be confusing that we're passing in other things as parameters in our traversal. Don't let that confuse you. You're still just doing a recursive traversal on the left and right, and you can just pass in, these are all pointers to the same list. So the recursion isn't creating many copies of lists. The entire time we are pointing to the same object. So if in one recursive call we mutate input list, that mutation will appear in other recursive calls that also use input list or whatever. Okay, awesome. Okay, we're back. Okay, so we're trying to fill out this function called common ancestor, and it doesn't seem that we're given any room for helper functions, so probably going to be doing this recursively because it's a tree problem, so we're going to have to somehow fit the recursion within this function. So another important thing to note is it returns an integer. Okay, so the main idea is, for how we solve it, let me go back to the example where our x and y are 6 and 7, is while we're traversing the nodes in the tree, if our node is equal to either x or y, we're going to return -1. So returning -1 serves as a flag because the problem states that all node values are non-negative. So if we get a -1, we know that down that path that we have traversed, there exists either x or y. So if you're at a node, say 21, and you recursively call sort recursive on left and right, and you get back -1 for both, then you know on my left side and on my right side exist x and y, so I am an ancestor of x and y. So then I could go ahead and return, find a way to return that. Okay, 21 is the ancestor for x and y, and if the first ancestor does this, then we'll find out the lowest ancestor for x and y. There's one other case where, say my x was 21, my y was 6. Then if one of my branches returns -1, so in this case 21 would be the lowest ancestor for this case. So I want to return 21. in this case, my right side will return 1 because 6 exists there. And then since I am one of x and y, then I am now the lowest ancestor as well. Okay? So those are the two cases we're going to deal with. Now, if you're not either the lowest ancestor or x or y, then you want to somehow return 0, and we'll see how that happens in the code. Basically, by returning 0, or it'll be more clear when I start writing out how this looks. Okay, so write it out here. First off, we're going to assert that x is not equal to y, so I can just add that at the top. Assert x does not equal y. Because we said that the elements are distinct, so we want to get two different elements, not the same element. Now, I'll add a flag for whether the node you're currently visiting is equal to either x or y. So Boolean here is equal to whether t.value is equal to x or t.value is equal to y. Okay? And then I'm going to recursively call common ancestor on my left and right subtree. So this is a similar pattern that we've seen in all our traversals. And I'm going to assign their return values to A and B. Okay, so common ancestor, t.left, xy. The xy don't change, of course. T.right, xy. Awesome. Okay, so now let's talk about the two cases that I drew above. If the return values of my two recursive calls are both -1, then I know either x or y exists in my left branch, and then either x or y exists in my right branch. So in that case, I know, okay, I found a common ancestor to x and y. So if a is equal to -1, and b is equal to -1, that satisfies the found a common ancestor. And then there's also the second case, which is if either a or b is equal to -1, and I am also here, which means that my current value is equal to either x or y. That's like a case where my x is 21, my y is 6, and it looks like this. Then the lowest ancestor would be 21, which is my current value. And then one of my branches would give me back -1. Okay, so those are the two cases in which we found a ancestor. So then in that case, I'm just going to go ahead and return t.value, because I want to return the value of the common ancestor at some point. So I'm going to return it here. Else, if here, then I'm going to return -1. So this is what we talked about, which is returning the -1 flag if the node you're currently at is either x or y. And then our final case is returning a plus b. Okay, let's talk about why we're returning a plus b. Okay, so say this 21 is the lowest common ancestor for something. Well, it isn't alone in the graph, so it could be a child of some other like nodes here, which has some other nodes, etc., etc. So since we say 21 is the lowest common ancestor, based off this if case, this node here would return 21. But when we're considering the viewpoint from the root, this is a recursive call. So this would, 21 would take on would be the value b for the root. So b would be 21 here. So basically the common ancestor is going to be either in A or in B, depending on whether my ancestor is in my left or right child. I don't know which one, so I get around this by returning A plus B and just ensuring that if I'm not a common ancestor, then I'm returning 0. So I'm going to be adding at the very end 0 plus the value of the common ancestor. So like all these nodes that aren't common ancestors and are not the values of x and y, I'm just going to return 0 for all of them. So then a is going to equal 0 here. And then at the very end, I'm just returning a plus b, which is equal to 21. So essentially the three values I might return for this function are 0, if -1, or the value of the lowest common ancestor, okay? And that will work just fine for this a plus b. So then I do need the base case. If t is equal to null, then I return 0. So that's where the 0 actually ends up coming in. So if I never end up finding, x or y, so like in this left subtree, then I'm eventually just going to hit my base case, which is null. I'm going to return zeros. If I do find the x and y, and then I find the lowest common ancestor, I'm going to end up returning my lowest common ancestor value up the tree until the root, which I return the final value. So hopefully that made sense. This is definitely, I would say, the trickiest problem on this discussion worksheet today. And again, you could do this recursively, just doing your traversal in an iterative fashion. Sorry, you could do this iteratively if you did the traversal in iterative fashion, but I won't go over it. Okay. Moving on to quadtrees. The problem states, say we're starting with an empty quadtree. Using the points below, what order of insertion into the quadtree produces a quadtree with maximum height and minimum height? Okay, let's start off with a maximum height. So the strategy we're going to be using is basically try to add the points in the order that produces the worst division of 2D space possible at every step. Because if you evenly divide the 2D space, then you'll sort of get an even distribution of your points into your 4 quadrants, and that will minimize the height of your quadtree. But if you don't divide the points evenly, then you'll have sort of like one point in the corner, and all the other points will be in one branch of the quadtree, and then you repeat that process. So that creates the tallest tree. So just looking at the graph visually, sort of the point that looks furthest away from all the other points would be -1, 2. So that looks like a pretty good contender. Let me just go ahead and actually label these A, B, C, D, E. Okay, so if I added A first, then that divides the 2D space like so. And you can see there are no points in the northwest, northeast, or southwest quadrants. So all the points would be in the southeast quadrant, so that isn't a good division of space. It's going to lead to a higher tree. So if I draw the tree, all the points will go down this branch. Okay, so what's the next point to add? The next point that would put all of the points into another subquadrant would be D. Because if I add D next, that divides the space like so. And then all the remaining points are in the northeast quadrant of D. Now, if I didn't add D, say I added E, or any of the other points, then 2 of the points would go in one quadrant, and then 1 of the points would go in the other quadrant. So this is not as good for getting maximum height. Okay, so I'm going to add D. So that would go here. Okay, then I have 4 children. The next point to add would be E. Because if I add E, that divides everything into this quadrant here. So go A to D to E. And then these last 2 points, I only have 2 points left, so it doesn't actually matter what order I add these 2 points in. So I could add C first, in which case I'd have C here, And then lastly, I have B. So that gives us a height of 1, 2, 3, 4. Or I could have added B first, and then C, and it'd still give us a height of 4. Okay? So that's maximum height. Minimum height is the opposite. So with minimum height, I want to add the points. And minimum height is what we normally want to go for. Maximum height is just telling us what we shouldn't do. So with minimum height, I want to add the points in an order that sort of divides the 2D space roughly evenly, or as evenly as possible. And if we just added the point C first, then C would divide the region into these 4 quadrants. And you can see all the other remaining points go in 1 quadrant. There's 1 point per quadrant. So this is a perfect division. We would just have C, and then in the upper left we have A, then B, then E, and then D. So this would give us just a height of 1. Nice, awesome. So you can see there's a big difference, or there can be a big difference depending on the order that you add elements. Okay, the last question is, given 5 points along the line, y equals x, an initially empty quadtree, how many different orders of insertion produce a quadtree of maximum height? So back to maximum height, but let's visualize what they're actually asking. So the problem is saying, say we have a 2D space where we have a bunch of points along a straight line. So say we had 5 points, like so. Let's think about what order of inserting points gives us a maximum height quadtree. Well, if we inserted this point first, that would sort of relatively nicely divide the points that we have into 2 regions. So that's actually not what we don't want to do. We want to do the opposite, which is dividing the points into regions where everything goes into 1 quadrant, as we did before. So if I selected this point first, then all the, oh no, I'm back. Then all the remaining points would go in the upper right quadrant, okay? Or, so you could either do that, or you could start off with selecting the most upper right point, because then all the remaining points would go in the lower left quadrant. So basically at every step, there's 2 points you could choose to give the quadtree maximum height, either the point on the lowest left or the point on the lowest right. So if I start out with this tree, or sorry, these set of 5 points, I could either choose this or I could choose this. So that's 2 options. Say I chose this, okay? So I had 2 options, but now I chose this. So my remaining points to divide are these 4 points. And now I again have 2 options. I could either choose like this point or this point. So I again have 2 options. So it's 2 options initially times another 2 options. And then say I chose this point, okie dokie. Now again, I have 2 options, either this point here or this point. Okay, say I just went ahead and chose this point. And now I have, again, 2 options. New color, nice, times 2. So I could choose either this point or this point. And then after choosing either this or this, I don't have any more options left because there's only 1 point remaining. So then I have like 1 option at the end. So in this case, I'd have 2 to the 4 options if I have 5 points. And you can do this exact process with as many points as you want. If I had 10 points, I would have 2 options, then 2 options, then 2 options times 2 options. This would be equal to the 9, right? So for a general n, the number of options you have for, or the number of different ways you can add things to the quadtree to produce a quadtree max height would be 2 to the power of n minus 1. Boom. Okay, that's it. I know this discussion video went kind of long. Hopefully this was helpful. Feel free to leave comments on Piazza, and I'll be actively responding.